Okay, so we move to covalent bonds. The big switch here is that our electrons are being shared between the atoms. Okay, the reason they're being shared is the difference in electronegativity between the atoms is small. Okay, the specifics of what small is we'll address much later in the semester. Okay, but ultimately we're sharing electrons. Because they're being shared, we don't see ion radii show up because they aren't ions. So there's no ionic radii. Okay, but the one thing that's kind of new that gets addressed with covalent bonds is bond length. So instead of looking at the individual radius of each of the component pieces, we look at the bond length. And what we note is that in a molecule, the bond length is shorter than the sum of the radii. Okay, so if we did that with hand gestures, and we'll attempt this, see if I can pull this off better. So there's two atoms, rough, crude fists. Okay, if it's an ionic situation, what happens? Bring them near each other, and what happens? One of them loses electrons. By losing electrons, what happens to it? It gets smaller. Where did that electron go? To the other one. And what happens to that one? It gets bigger. Right? That's what's happening with our ionic systems. What's happening with our covalent? So I have my two atoms. I now bring them near each other. They're sharing electrons, which means some of these guys, my right hand's electrons, have to interact with my left hand. Okay? Which means my fingers, the outermost parts, need to overlap. By overlapping, what has happened to now the distance between those nuclei? It's gotten a little bit smaller than if we had looked at them not interacting. That's all we're saying. Okay? So mathematically, if you take radius 1 plus radius 2, that answer is a larger value than what the actual bond length is. So 0.136 versus 0.127. The actual bond length is a little bit shorter. Right? And that's just because we're sharing those electrons. So it's a slightly different process than our ionic bonds. That's about it. They never overlap orbitals, is what I'll say, which is kind of a cop-out in your statement. Okay? We're going to skip bond energy altogether, so let's not worry about it, which gets us to our Lewis structures, okay, for molecules. And I made some edits, and I don't think I made them to this PowerPoint. So here's what we're going to do. I'm going to give you a second. How many of you read through the that thing with pages in it? The textbook. Thank you. The textbook rules for Lewis structure. Yeah? Okay. Compare them to these. Or if you learned Lewis structure somewhere else, see if you can identify how my rules are different than what you've learned in the past. And it may be helpful if we look at an example, which I plan to do. You can write it, yeah.
Write it down. What are the similarities and differences between your past knowledge of Lewis structure and Mike's rules?
Structures, at least for those people that already have some Lewis structure knowledge. Anybody note any differences? Notice anything? One big difference I can point out shows up in Rule 3. See the word electronegative, right? We talked about electronegativity in the lecture, right? Anybody tried to find that in the textbook? It's not there. Electronegativity as a concept is not even in our textbook, okay, which I find baffling. Okay? So that's one really big difference, okay, between my rule set and what our textbook presents. They actually don't talk about electronegativity. Arguably, electronegativity is what dictates Lewis structure. So why can the textbook take out electronegativity, that would get back to what Greg was talking about earlier, the heuristic versus the algorithm versus the code. Most everybody is taught the code for Lewis structure, but they have no idea about the background behind it, which is great when all you have to do is solve general chemistry. When you actually have to apply that structure to any future class, you fail miserably. Okay? And then everyone goes, oh my God, it must be OChem's fault that it's so difficult. No, you were just taught Lewis structure incorrectly. Okay? So, electronegativity is the really big differentiator in here. And then the next big one is looking at resonance, an insanely difficult concept, particularly if you follow how it is typically presented in textbooks or online, the internet, and all sorts of other fun stuff. Okay? In that video that in theory you went through and watched, you were forced to watch this section on formal charges, which was like 5 to 10 minutes long. I apologize. You are not responsible for formal charges. That's just an artifact of not realizing I could shorten that out for Chem 130. Right? So your knowledge for formal charges is you just assign non-zero formal charges in the upper right-hand corner. You keep it nice and simple. Okay? Once you've done a Lewis structure or built a Lewis structure, you can then apply more information to the top of that. That more information comes in the form of shapes. So you could go through and now evaluate what is the shape of the molecule, both as an electron geometry and a molecular shape. Slightly different meanings behind those. We'll address those when we look at an actual example. What is shown up in this shape summary is what you are responsible for. You need to know everything that is memorized or written up there. Okay? And one of the things that makes things challenging for chemistry, particularly in that video we just watched on memory recall, oh, I can just memorize facts. Very little of chemistry is actually memorization of facts. It's the application of those facts to a different system. Right? This is raw facts. I don't ask you to recall this. I ask you to overlay this content on top of a structure. Okay? So you have to be careful in that process. It's not just a fact. It's how do you apply that fact to an entirely new question. Okay? Which sets us up with my shortened version of the rules, okay, where I tried to boil it down to the bare essentials without any real descriptions. Okay. And now we could potentially work some practice. The play posit looked at CF4 and SO3. Okay. I would argue we could do new problems. Carbon, methane, ammonia, ammonium hydroxide. Don't worry about the names. Okay. Any of those you would like to see. Did you watch the Lewis structure and are like, I didn't understand how you did that one? We can do that. What'd you get? Hydroxide. Okay, should we just go into it? Okay. So we start. Total the valence electrons. So that means look at all the atoms in hydroxide and tell me the valence electrons. So, first symbol is oxygen. How many valence electrons does oxygen have?
6.
It has 6. We know that because... What's that? I like the
group that it's in.
The group that it's in. Oxygen, if we look at the Roman numeral directly above that column, it says V1, which is 6. Okay? So it has 6 valence electrons. Hydrogen. How many electrons does hydrogen bring in? 1. Okay. The next part is kind of challenging here. The new thing on this would be, what the heck is this minus doing there? Upper right-hand corner means what? That's charge. Okay, so the balance of protons and electrons are unequal. That's why it is charged. If they were equal, we wouldn't write anything there. When oxygen comes in with 6 valence electrons, it's coming in neutral. When hydrogen comes in with 1 electron, it's coming in neutral. How did I get a -1 charge?
There's an extra electron.
I add an extra electron into my total. Okay? That's how it became negative. So I have to account for that extra electron. What if it said -2? I add 2 electrons, -6. You add 6 electrons in. Okay? We add that up and we get 8 electrons. Next rule, pick our central atom. The central atom is usually the least electronegative. With the example we're looking at with hydroxide, it's 2 atoms. There isn't really a center atom, so it's not a really big deal. Okay? Typically what we would do is circle it around the one that had kind of more electrons around it. Hydrogen can't act as a central atom. Okay? A central atom, the whole point of being in the center is to bridge things. Hydrogen can only have 1 bond, so it can't bridge. Okay? That's more like a plank. That doesn't work. Okay, so oxygen is better defined as our center atom, so I'll go ahead and draw my oxygen. One of the extra steps that I would go in, which isn't in the list here, but can be helpful when we deal with shape, is remembering that Lewis structure, or Lewis built his theory off of cubes, okay, which is really just a 3-dimensional square. So draw a square around our center atom. Okay? I will then place the other atoms around that square, ideally placing them on the face of the square. So I'll place my hydrogen here. Okay? It can be on any one of those 4 faces, okay, but that's the easiest one, okay, for me. What's the next thing? Rule 3 comes after rule 2. I need to add electrons to the most electronegative. Which atom is more electronegative, oxygen or hydrogen?
Oxygen.
Oxygen. So I'm going to start placing my electrons to the oxygen. Okay. I'm going to put the first pair between the oxygen and the hydrogen. Why? Because I know there needs to be a bond there. Okay. If I didn't have electrons there, there wouldn't be a bond. Okay. So I'm going to place the first pair there. The next pair doesn't really matter. And I'm going to place until I've achieved the octet. Okay. Octet for 8 electrons. I need 8 electrons around every atom. Okay. Which sounds a little bit weird, but we'll address that in just a second. Okay. Any place that I now have a pair of electrons between, or actually, sorry, continue adding to total electrons. Do I have more electrons to add? How many electrons am I allowed to add? 8. How many electrons have I added? 8. So I'm done adding. Okay. Anywhere that I have a pair of electrons between atoms, I will turn into a line to represent that bond, connecting them. Okay. And now I'll check octets. How many electrons around the oxygen? 8. Okay. Hopefully we can clearly count the non-bonding pairs, the free dots. The line gets a bit tricky. That is 2 electrons in that line. Oxygen has access to both those electrons because it's shared back and forth, okay, which means there's 8 electrons around the oxygen. Does it have an octet? Yes. Oct for 8. Like an octopus has 8 tentacles. You know. How many electrons are around the hydrogen? 2. Are there 8 electrons around it then? No, there's only 2. Okay. Hydrogen can only fit 2 electrons around it. Why can it only fit 2 electrons?
Because it only has the orbital S.
For a hydrogen, it only has the 1s orbital. That's the only energy level it really has access to. How many electrons can I place into that lowest energy orbital? 2. Okay, so hydrogen's octet is 2. Some people will refer to it as a duet. You might hear that float out there as a term. I don't know why. I just call it its octet and put air quotes. Okay? Yes?
Is hydrogen the only exception there, or is there other?
Is there another element that might be an exception to that?
Like helium?
Helium would also be an exception to that.
So does
Okay.
that one only do 2 as well? Or I understand.
It could only fit 2 in its outermost orbital.
Okay, but the
Yeah.
rest of them can fill 8.
The rest could potentially fill 8. The metals get trickier. You'll notice that when we go through and look at these, take a look at all of the structures that are listed as examples. What do you notice for those? They're all non-metals. As far as you guys are concerned, all of our Lewis structures are nonmetals. Okay, don't bring the metals into it. Okay. It does make it a little bit more complicated. We could, but it's just not worth the trouble. Okay, so we're only doing this for nonmetals. So now what do? Okay, I've satisfied octets. I don't have to worry about resonance. Okay, 7 is crossed out only because I gave you a formula. Don't worry about the formula, but we do have to specify the formal charge. Based off of that previous slide, how do we specify the formal charge? Okay, we put brackets around the whole structure and we put a -1 in the upper right-hand corner. That's it. Okay. If you wanted to make it more complicated, you could specify what atom had the negative charge. You are not responsible for that. Okay? I would also argue you are not responsible for drawing all the brackets because that's a lot of work. And you will also sometimes see me draw that. That is not -7. That is a half bracket that I was too lazy to finish drawing and a minus sign. That is perfectly acceptable, okay, for this class. Okay? What do we now have drawn? The Lewis structure for that species. We've answered that question. Okay? What if I wanted to evaluate its shape? And by what if, let's do that. Okay? In evaluating the shape, I want to find my center atom. This is why I put a box on the center atom. This helps zero in so that someone grading it, like me, would know that that's what you're talking about. Because if you don't put that box on there, it makes it more difficult to go through and grade, okay, and potentially getting you marked wrong. If it's a multiple choice, how can I make sure that you're picking oxygen as the center atom? Yeah, by telling you it's the center atom. Okay? One way I could draw your attention to it is in the formula, I could bold the oxygen to help emphasize the fact that that's the center atom.
So you're saying that the box is a visual design element that helps you draw focus to the most important piece of information?
That would be correct.
A key piece of information?
That would be correct. We're looking at the visual design of Mike's system, which gets very crowded very fast. Okay? Which is why a lot of people don't teach it this way. So, what do we now do? Well, to decide our shapes, we have to evaluate groups of electrons. Okay, so this is where the box comes in handy. I look to the top face of that box. Are there electrons there? Yeah. Are there electrons on the left face? Right face? Bottom face? Yes. How many groups of electrons are there? 4 groups of electrons. 4 groups of electrons, according to that table that you guys have now memorized, corresponds to what electron geometry? Tetrahedral. Okay. This is now the electron geometry. It's only called the electron geometry because I have not distinguished between what's in those circles. Okay. If I now double back and say, well, actually, I drew that as a line and that as 2 dots. Did I signify those as different things? Visually, are 2 dots different than a line?
Yes.
Yes. Did I symbolize them as different things? Yes. Okay, so now I want to address that when I look at the overall shape of the molecule. Okay, in the shape of the molecule, really all I'm concerned about are the atoms that are present. In this case, it's relatively straightforward, but in other cases, maybe not so much. You would look at each of those groups and decide, are they bonding groups or non-bonding? The bottom group, is that in a bond? How do you know that? Not aligned. Left? No. Top? No. Right? Yes. So that says 3 non-bonding groups, 1 bonding group. What shape does that become? To be honest, I'm not sure that's actually even in the list. Anybody actually print out the slides? I'm not about to reverse backwards. It's going to delete all my work. Oh, it does show it? Oh, cool. It's a linear shape. You mean if I kind of blur my eyes and only look at the atoms, the shape of those atoms is linear? There's literally only 2 points. What shape has 2 points? A line, that's it. That's why it's a line. Okay, so the linear shape becomes obvious in that case. Okay? Who decided what those names were? Tetrahedral or linear, or trigonal pyramidal, or trigonal planar, or bent? Who got to decide that? Somebody probably old and dead. Okay? They came through and said, this is the shape because it best looks like it in my opinion. Everybody has to listen to me. So you are responsible for knowing those shapes and those specific names. If you have to move into further chemistry classes, the table, which I think I can flip back to before we get to that, are we okay with everything that's up there? We flip back to it. Could we have more than 4 groups of electrons?
Yes.
How many faces are on a square? 6. There's the front face and the back face. So there aren't just 4 groups of electrons. We could go all the way up to 6. So we could have 5 groups and 6 groups. Each of those are then going to have the same kind of breakdown in bonding and non-bonding. Each of those then has their own shape name, and you get all sorts of other weird, bizarre names coming out of them, like the T shape. Why? Because it looks kind of like a T. The seesaw. Because if you turn the molecule just right, it looks like a seesaw. Okay? Those names were entirely arbitrary and just kind of picked out of thin air because whoever saw them saw that first. Okay? You are not responsible for those for this class. You go up to tetrahedral. Okay? Yes?
So on that last element that we
You'll notice I didn't put that in there.
identified, would it have been just linear or tetrahedral? It falls in the group of tetrahedral.
Xenon Tetrafluoride, I believe is what you're asking about? No? Oh, which,
I mean, go back to the oxygen,
for this one?
Yeah, like the last one we did, one bonding group. and three
1 bonding and 3 non-bonding is linear.
But that would be the same as one bonding, 0 non-bonding. So it's-
Does it get you the same shape? Yeah, it still has the group of tetrahedral, the subcategory of tetrahedral. But the end name for the shape becomes linear. And that's going to depend on what you care about. It could very well be that these 2 linear or all of those linear shapes, and all you care about is the linearity of the shape, then you would just call them linear and you would have no distinguishing feature on the other end of it.
So for
You wouldn't even identify it.
if I were to answer that quiz, would you prefer tetrahedral linear or just linear?
Just linear. Yep. If I ask for molecular shape, all I'm asking for is that name. If I ask for electron geometry, that's what I'm asking for. You'll never get a blend.
would you lose points for giving tetrahedral?
No, you wouldn't lose points for specifying it either, because it's right. If you specified wrong, like for that hydroxide, that OH minus, if you told me that it was linear, you might get out just because I was like, why are you repeating yourself? But if you told me trigonal planar linear, I might take off points because trigonal planar is wrong. Does that make sense?
Of course, me as a writing guy, I'm like, all the words, put all the words.
Yeah.
But I'm not, so.
Okay, so there's hydroxide. Hydroxide's off the list. Want to try another one?
Bottom one.
Bottom one, NH4. How do we do NH4?
Assume that nitrogen is the center.
Nitrogen, center atom is step 2. I don't care about step 2. Step 1, valence electrons. Nitrogen has 5. Hydrogen has. Do I have a charge? Yeah. So I have to evaluate the charge in, oh yeah, sorry, your 4 hydrogens. I have to evaluate the charge. I now have a positive charge. How did I become positive? Okay, I added a proton. Could we add a proton? No. Protons change the identity of the elements. You cannot add protons. You also cannot remove them. The only thing you can add and subtract would be electrons. Okay, so to get a positive charge, what did I have to do? I had to subtract. I had to subtract an electron. Okay, which is tricky. I'm subtracting, and yet what happened to my number? Became positive. Again, why? What am I subtracting? A negative thing. So knowing the charges of these things and their relative masses is very important to being able to answer questions. It's all about the application of that knowledge. So 5 plus 4, 9 minus 1, 8. So again, we started off, our hydrogen can't bridge, so nitrogen's our center. There's our box. Of course, I decided to switch the colors, because why not? Hydrogen, 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 hydrogen. Where do I start placing electrons?
Just draw lines
Okay.
everywhere.
I would argue you should always just go through and start placing electrons. Okay? So, electrons, 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 electrons. Some people are like, that's redundant, because I know all you're going to do is go through and erase all of those lines, and you just made me erase a bunch of stuff. If you get it right, I can't complain. If you get it wrong, what I'm going to ask is, did you actually show the electrons? Because more than likely what you did is you over-added electrons. Okay? Does the nitrogen have its octet?
Yep.
Yep. 2, 4, 6, 8 electrons around it. Does the hydrogen have an octet? Remember, hydrogen's octet is only 2 electrons. We're done. Okay. Last step in this one. We're going to put our parentheses and the plus sign. Okay. What is the molecular shape? We check groups of electrons all the way around. How many groups of electrons around the nitrogen? There's 4 groups of electrons. 4 groups of electrons for an electron geometry means tetrahedral. For my molecular geometry, what do I need to do? I evaluate bonding versus non-bonding. All 4 groups of electrons are bonding, which means my molecular shape is also tetrahedral. Ta-da! Kind of makes sense? I'm going to argue NH3 and CH4 are the same. I'm going to be kind of irritating and point out carbon. Okay. And this is where I think the root of all of the failures of Lewis structure descriptions in the past comes from. Okay? If we were to go through and draw the Lewis structure for just a carbon atom, how many valence electrons does it have? It has 4 valence. Okay? When we go through and draw this, believe it or not, this is how we would draw it. Okay? Just countered my rule set, right? With my rule set, I said we should pair them. When we go to atomic structure, we don't pair them right away. Why in the molecular structure would I pair them?
Symmetry.
In a molecule, what do I need to make? Bonds. How many electrons are in a bond? 2. Do I need to make bonds for a single atom?
No.
By definition, not. Which means when I go through to place my electrons, I want to place them as far away from each other as humanly possible. That's why they go unpaired. Why does this then become a problem? Well, because somebody went through and said, well, it's effectively a Lego. Because if I look at hydrogen with only 1 electron, I can then smash these together as bonds and put in 4 hydrogens, which is a phenomenally cool observation, and I kind of agree with that philosophy, until you have to apply that knowledge into something like resonance, in which case everything just went out the door and your theory crumbles into an abysmal pile of crap. Okay? And for those of you saying, wow, it's a bit dramatic, it is not.
Just vivid words.
Okay? It is actually fully correct. Okay? And why would I care so much? Virtually everything we do in organic chemistry has to do with resonance, Okay? By teaching you incorrectly how to draw a Lewis structure in Chem 130, you propagate that horrible knowledge through up to OChem, and I have to reteach you everything when it gets to resonance. And it becomes a nightmare for both you and me, because we keep going in circles. But I wanted to do it this way. Sorry, your teacher taught you wrong. Okay? When we go to build a molecule, everything changes. It is not just a single pool of electrons that belongs to an atom anymore. We total the valence electrons to get the electrons that belong to the entire molecule. Where the electrons go in the molecule has nothing to do with the valence electrons of any given atom. It has everything to do with electronegativity. Right? Because electronegativity is the ability for an atom to attract bonding electrons towards it. Okay? So the rule sets change when you look at an atomic Lewis structure versus a molecular Lewis structure. How useful are atomic Lewis structures? Not at all. They are utterly meaningless except to set up the false presentation of Legos. Okay? So, let's take a look at one that was in the video, CO2. I personally find this one really fun. And that hydrogen's kind of irritating, but it's not showing up on my screen. Close enough. How many valence electrons does carbon have? 4. How many valence electrons does oxygen have? How many oxygens are there? 2. I total this up, what do I get? 16. This, by the way, is going to draw attention to why this method is different than the method you were taught. What's our center atom? It's going to be the carbon. So I'll put my box around my carbon, and I'll draw on my oxygens. Does it matter where I place the oxygens? At this stage, no. It's completely irrelevant. Okay. I now need to place my electrons in here. Where do I start placing electrons? Around the carbon, he says. Okay. No, we do not place them around the carbon. We want to go around the oxygen because the oxygen is more electronegative. Okay. Carbon is not more electronegative than oxygen. We should place them on the oxygens first. I will place them in the space closest to the carbon because I know I need to make that bond. How many electrons have I drawn into the structure now? 16. Now I can go through and erase and make my bonds. How many electrons are on each of the oxygens? 8. Have we achieved an octet? Yeah. Okay. How about around the carbon? No. Mistake number 1. Okay, well, let's give it some more electrons. That's wrong because 16 valence is all I'm allowed to put in. By adding 2 electrons or 4 electrons in that fashion, we've increased the number of electrons beyond the count we were allowed. Okay, so what do we do? Okay. Satisfy the octet by moving pairs of electrons. Where do you see a pair of electrons? All around the oxygens. Okay, so I'm going to take this pair of electrons and I'm going to move them to the carbon. Carbon now has more electrons, right? It's getting closer to satisfying its octet. But at the same time, what did I do? I took them away from the oxygen. So I might be fixing oxygen or carbon, but at the same time I'm ruining oxygen. Where do I move the electrons? I'll move them into the space in between. Okay? I now have a pair of electrons between atoms, which means double bond. I have another line. I now have the formation of a double bond. The double bond does not exist because someone said there's a double bond. The double bond exists because carbon needs its octet, so oxygen shared. That's why it's there. Does the oxygen still have its octet? Yes. Does the carbon? No. We'll get to that. Okay. So carbon's still missing its octet. So what can we do? We'll move another pair of electrons. Which electrons do we move? Okay. We could go from the other oxygen. Does our original oxygen not have a pair of electrons? Couldn't it move those in? Yeah, absolutely fair game. Okay. The result is this now triple bond between carbon and oxygen and a single bond to the other oxygen. Is this structure invalid? No. Okay. It's not pretty. You may not like it. Do you know why it's not pretty? Okay. We could run a symmetry argument. Ultimately, the symmetry argument isn't going to hold as much water as another argument goes. That other argument is formal charge. If you go through and assign formal charge to atoms, you will find that this structure generates lots of formal charge, thereby making it a worse Lewis structure. Does that mean it doesn't exist as a structure? No. This is the concept of resonance. There's multiple ways to represent the same compound. Okay? So one suggestion was, couldn't we have gone through and done this with the bottom oxygen? Right? Which I know this was not what you were suggesting, but I'm going to say you were suggesting this anyway. To this level at least. Right? What is the difference between those structures? Can you tell that they are different? Yes. Okay, done. So they're different. Resonance, you can't spin, rotate, flip. It is locked in place. Okay, like you dissect a frog and you pin down the parts. I've never done it. Well, I haven't done it for a really long time, but as I understand, that's what you do. Same thing's happening with Lewis structure. It's pinned down. You can't spin it. Triple bond is aimed down versus to the side. Okay, both of those structures need to be represented for this. Okay, because they're both representing the same atom or the same molecule, just a different arrangement of the electrons. Was there another way we could have done it? Okay, in black, we have yet another way we could have done it. If I asked you to draw the Lewis structure for CO2, which of these answers would I expect you to draw? All three. Okay. If you take higher level chemistry classes, your teacher had better explain why those triple bonds are bad options. If they don't explain it, then they had better take credit for it. Okay. And I would bet most of our instructors won't explain that properly. Okay. So we have to be careful on understanding why we do patterns the way we do them. Why is it important to be aware of the triple bond structure? When I make CO2 react, it's equating to the triple bond structure. That actually shows its chemistry and how that molecule reacts. Okay? Lewis structure gives me that information. If I only look at one resonance structure, I lose that content, I lose that knowledge. More structures allows me a better flexibility to understand that reactivity. Okay? Yes?
So in the triple bond structures, you have the two oxygen plates right next to each other, and on the other one, it's the sun.
Yeah, I thought you were going to complain about that.
I was just wondering if the latter would be still correct. Yeah.
Is drawing this now a distinct Lewis structure? Or is this another resonance contributor? Are these resonance of each other? No, those ultimately aren't resonance, unfortunately. Okay? When we draw out our Lewis structures to find our resonance, pin your atoms, don't start moving them. So that was bad of me to go through and shift to that. Why did I start to shift to that? What's the next question after we do Lewis structure? The shape. Okay, so I would go through and look at the shape. Okay, center atom on my carbon. Actually, let's not do that one. Center atom on the carbon in black, the bottom. Are there electrons to the right? Yes. Are there electrons to the bottom? Are there electrons to the left? Electrons to the top? No. How many groups of electrons? 2. What shape does that mean? Linear. Did I draw that molecule in a linear representation? No, I drew that kind of triangular-ish. Okay? So my drawing doesn't accurately reflect the shape. This is where Lewis structure kind of falls apart. Lewis structure doesn't predict shape or how the molecule looks. It just says where things are connected and how electrons can move through the structure. If I want to layer that information on top and look at both the connectivity, Lewis structure, and electron flow, and the shape of the molecule, I can redraw it to better represent that linear shape. Okay? When we draw structures, should we be drawing them as close to the actual structure as possible? Okay, I'm going to draw a conversation of 2 humans talking to each other. For those of you that missed that, because I did that kind of fast, can I erase some stuff? Yeah? Okay. There we go, in purple. That is my conversation of 2 people talking to each other. Can anybody tell that that's 2 people talking to each other? No. In the process of trying to communicate my ideas to somebody else in the world, what might I want to try to do? Be as clear and obvious behind that presentation as possible. That's why we're trying to best reflect the correct 3-dimensional structure. So we can use Lewis structure as a way to kind of sketch out our work as a first draft. Once we have our draft and realize that we drew it incorrectly, we could fix it to better represent that structure. And I could potentially redraw people, but that's a bad idea. Clearly. Does that make sense? Okay. If you have another method for doing Lewis structure, you're more than welcome to share it with me. Ultimately, I'm probably going to find out where it fails is in dealing with resonance. Okay? And what it'll come down to is that you memorized a pattern. A lot of people can draw the structure of CO2 and look at the one with the triple bond and go, oh, you can't do that. You ask, why can't you do that? And they're like, you just can't. That's not a valid answer, guys. Okay? There's a reason for it. You have to be aware of that reason. Okay? Exam purge. This is our big kind of purge thing. Again, it's in the slideshow. All you've got to do is open up the slideshow. It's the very last slide. I would highly encourage you that when you're allowed to start the exam, you tear that first page off, periodic table, you dump this information. Okay? We've got electronegativity, ionization energy, and atomic radius. The bulk trends. Notice I also have valence electrons circled and highlighted at the top. Okay? Arguably, there's another layer of information we could drop on this. What's that extra layer? Anybody figure it out yet? The charges, you're responsible for charges. This is a +1, +2, +1, +2, +3, -3, -2, -1. Who's saying the charges aren't that big a deal? It may not be that big a deal on this exam. As soon as we move to nomenclature, it becomes huge. You need to remember your ionic charges. Okay? After that, what do you guys have questions on? You don't have any questions, that's, I guess that's fine with me, but.
So in the event that we can write it in a better way and don't on this particular exam, you're not going to take it?
No.
Yeah, so we don't have to write it.
You do not have to draw the correct 3-dimensional structure. What I will ask for is what is Lewis structure? give me the Lewis structures, and then later on I'll talk about shapes.
Okay.
But
So-
we have to draw like for CNC with all three of those.
For Lewis structure, yes, you would have to. For a shape, you wouldn't have to. All you would need is one, and believe it or not, all three of them get the exact same shape.
Which light emission is most energetic? Or are they all equally energetic?
Okay? We're talking about light. Light is part of which or what thing? Our electromagnetic spectrum. In fact, I'm not going to attempt to draw this. In fact, because we got slides, you might close your eyes if you get dizzy. We're looking at our energy spectrum or our electromagnetic spectrum. Okay. Cosmic rays, gamma rays, X-rays, ultraviolet, those are all high energy. That's why when you go to get an X-ray, the tech is never in the room with you. They like go hide behind a wall. They're hiding behind a wall because they don't want to get hit with the X-rays. Okay. Why are you getting okay to be hit by the X-rays?
You're only doing it once.
You're doing it once. Okay? A tech would be hit by those same X-rays again and again and again and again, and that would cause damage. We're hoping that the cost-benefit analysis of taking an X-ray to find out what's broken in you is more important than potentially maybe kind of causing cancer. Okay? That's the benefit between those. Okay? Ultraviolet and then our visible breaks down, starting with purple, also known as violet, so it's closest in energy to our ultraviolet, which will scan all the way down through our colors out to our red, which is closer to our infrared. Which was higher in energy, our ultraviolet or our infrared? Our ultraviolet, so the closer we are to the purple end of the spectrum, the better off we are. You'll notice that in a multiple choice question, I don't give you the spectrum. How would you know what the spectrum was? This is our memorization. You'd have to know. Roy G. Biv. You could argue backwards, or we could just say violet was high energy and low energy. Right. Now you'd be able to align those. Other questions?
Is purple a color?
Purple's not a color.
Purple is absolutely a color.
No, just like, it's, pink isn't like a color, it's a tone.
Don't talk about purple.
Like when you take color theory, they tell you right off the bat, purple is not a color.
What
It's
about,
indigo. It's
is-
indigo.
Is 11111 a color?
What?
Is 1, 2, 3, 4, 5, 6 a color? It's the hexadecimal color system that computers use. So whether purple is a tone or not depends on whose language you're using and what they're emphasizing. The paint wheel is different than the light wheel.
So,
is different than
according to your color people, we don't care about your color people. Purple's a color. So when we talk about scientific method, okay, I went through, we had talked about all those different steps, and then I made my claims about something. What did I say was the most important? Failure is my opinion of what's the most important. Right. I've received lots of questions about this one, so we could pull this one up. Tell you know about what? Oh.
Do I believe in flat Earth?
Whoa! I'm not saying that.
Whoa! It's a bad thing.
No,
There's
everyone's
no
entitled
science
to,
anyways.
everyone is entitled to their opinions in this world.
Yes, and some opinions are
Some of those opinions are wrong.
Some opinions are wrong.
Lead
I
206.
see it the type. Anyways, Mike.
How many protons and neutrons does an atom of lead to yeah, I just got triggered. Lead 206 have? It does not have 206 protons.
Okay, then now I because that's what you told me.
That is not true. I did not tell you that. It has 82 protons. How do you know lead has 82 protons? I know that lead has the symbol of Pb, and when I look up the Pb on the periodic table, there's an 82 above it, which represents the atomic number. And according to like 5 slides earlier than that, the atomic number is the number of protons. So the number of protons for lead 206 is 82. So if I tell you lead 206, you can tell me the number of protons is 82. You can also tell me the number of neutrons, because what does that 206 represent? It's mass number, not its atomic mass. I know it's a subtle difference, but it's the mass number. The mass number is protons plus neutrons. So I do the math, 206 minus 82, and I get 124? I'm just trusting somebody else. That's all I'm saying. And I now know the number of neutrons. That's what that notation means. It gives me that information. Okay? So if we switched it to the question, which of the following does not exist? And I said carbon, that says carbon, 14. Nitrogen 14, or phosphorus 14. So number 1, and then we list out some other answers like all of the above and none of the above, because those are always irritating. I have had people go through and say, it's never none of the above. That is a complete and awful lie. That is not true. There are plenty of questions where you will have none of the above as a valid answer. Same deal with all of the above. Okay? So just because it says none of the above, do not start eliminating that answer. That is a bad, bad process. Okay? So if it's carbon 14, so in these notations, we're told we could get the number of protons and we could get the number of neutrons. Right? So what are the number of protons that carbon has? 6. How many neutrons would it then have? 8, right? 8 plus 6 gets us our 14. Okay? And just because it happens, you are allowed a calculator. You should bring a calculator, and you should assume you can't do math. Okay? And I'm not making assumptions about your math abilities. On a test, you will freak out. You will screw it up. Use the calculator. Okay? At worst, it's you spent an extra 10 seconds. It's not that big a deal. Just do it.
400 seconds is more of a big deal. That's almost 7 minutes.
7 minutes on an exam that you won't need the full time for in all likelihood. So it makes sense to spend the time there. Nitrogen 14. It has 7 protons. How many neutrons? 7. Phosphorus 14. How many protons? 15. How many neutrons? -1. Can you have less of a piece of matter? No, that doesn't happen. Okay? For that matter, if I drop to 14, we just ignore this negative aspect in there. Okay? If I had 14 protons, would I be phosphorus? No, I'd be a different element because the number of protons define the element. So if I had 14 protons, I'd be silicon, not phosphorus. This name makes no sense. Right? So the answer becomes phosphorus 14. That is the only one that is impossible. Okay. Carbon 14 and nitrogen 14 are both common isotopes. I was going to say carbon 14 is used for radio dating, but it might be carbon 13. It is carbon 14? Okay. So yeah, carbon 14 is actually used to date materials. Right. Not like relationships. I saw you thinking that. Okay. To tell how old they were. Okay. Nitrogen 14 is the more common isotope of nitrogen. Other questions? Okay, so the first thing we're going to do, I'm going to try and get to a slide that's actually relevant and not reveal too much information at the same time, which I've probably already done. So, there are atomic fingerprints. So the atomic line spectrum. Atomic line spectrum come from what? It's the wavelength of light emitted when what?
Electrons go down.
When electrons jump. What did Rutherford discover?
That they have different colors based on how the orbitals they drop.
What was Rutherford's experiment? Gold foil. What did the gold foil experiment prove? The existence of a nucleus. What is in the nucleus? Protons and neutrons. What is moving with atomic line spectrum? Electrons. Does Rutherford's experiment have anything to do with atomic fingerprints? No. They're two entirely different classifications. Rutherford's looking at the nucleus. Atomic line spectrum are looking at electrons. What's the sciencey name? Scientist name tied to atomic line spectrum? That's Bohr. Okay. Niels Bohr. Bohr was a discrete gentleman, is my fun phrase. Discrete meaning there are distinct energy levels. And he's a man. So. Gentleman.
We learned about the lines.
Yeah, I think it works. Other questions?
So on the practice exam, there's a lot of the, like instructions, like read through everything, make sure you write your name on page 4 at the bottom. Is that going to be like our exam? Okay.
Yes.
Just make sure it
I
has
gave you the
that.
practice exam to give you a feel for what your actual exam will be.
Okay.
For those of you that are snickering and laughing, you probably read the practice exam. It's probably a good idea to read the practice exam. Yes. Oh. 3, 4, 5.
So 3, 4, 5 are still valid?
Yeah. We have to go back up to them. They're ways up there. They're like the very first slide, aren't they? Oh my God. So the first one was that they're indivisible or indestructible, which is proven false because we have subatomic particles, protons, neutrons, electrons. Okay? All atoms of the element have identical properties. Isotopes disproves that because they have different masses. Electrons disprove that because they have different charges. Right? Atoms of different elements combine to form compounds. Can I combine hydrogen and oxygen to make a new compound? Yes, I get water. Compounds contain atoms in small whole number ratios. Can I take half of an atom? No. So whole numbers just means 1, 2, 3, whole numbers. Okay, no decimals. Atoms can combine in more than one ratio to form different compounds. Also true. We can take H2O, or let's see if I can pull this off. Two people walk into the bar. The first guy orders H2O. The other one says, I'll have H2O too. The second one dies. Da-da. Yes. Okay. So yes, we can combine them in different compounds. I actually said that one correct. I'm impressed. I usually botch that thoroughly. Other questions? Wow. That's a rough statement. Other questions? Yeah.
Can we just do a quick example of like element X given the abundance type of problem?
That involves lots of math. So by quick example, do you mean, can you show me the example so that I
Yeah.
can do it? Yeah,
Yes,
we can do
please.
that. So element X, we'll call it X6 versus X7, I believe is what it was.
Yeah.
Because I don't remember any of the numbers. So
Yes, I have it right here if you need it.
we might very well do that. We have mass, and then we have percent. Yeah, reflective glare didn't work out so well for me there. The mass of 6 was 6.015. The mass of 7 was 7.016. And the percent of 7 is 92.5. Calculate the atomic mass. What is atomic mass?
Average mass between isotopes.
Okay, the atomic mass, or the atomic weight, which is what we find on the periodic table, is related to the mass number, but it's not the same. Okay? It is the average mass of all isotopes. Okay? Well, I could go through and take the average mass. 6 plus 7 divided by 2, I get about 6.5, and we get the wrong answer. Okay? It's not just an average mass, it's a weighted average mass. Okay? And when we look at a weighted average mass, what we're talking about is the percent of 1 times the mass of that same 1 plus the percent B times the mass of B. What would this then equal? Our atomic mass. Okay, are we given the percent of A? Okay, well, we weren't really given A and B. We said X6 and X7. So what could we go through and do?
Subtract 92.5.
We'll do that in a second. We weren't really given A and B, so what could we do? X6 is A. X7 is B. So I could go through and start to plug numbers in, and I might find right away I don't have the percent of A. What was the suggestion?
Subtract 92.5 from 100.
If I take 100 minus 92.5, I would get the percent of A, which was 7.5%. Which is an important thing to add there, are percents. So now I could drop that information in. Our percent of A is 7.5%. Use the Greek language to help us out. I think that's Greek, Latin, Greek, cent. One of the two? Okay.
Yes.
100. So per 100, what is the mass of A? 0.15 plus the percent of B. What was that one? 92.5% times the mass of B, 7.016. I do the math, I'm straightforward, I just now plug and chug and get the atomic mass. Okay? How else could the question get written? Or could the question get written another way? Is this how we solved it in class? No, it is not how we solved it in class. We used an entirely different process. Same formula, but we gave you different pieces of information. Okay? So what you need to do is realize that just because you have a formula doesn't mean you're always going to be solving in that same linear fashion. Okay? A lot of stuff we will be encountering will be algebra based. Okay? In this question, or in that equation, you were given 4 pieces of information, all of them on the left-hand side. You will always be given 4 pieces of information because you can't solve for the 5th unless you have 4 pieces of information. Do those 4 pieces of information all have to be on the left side of that equals? No, I could take 1 from the right and then 2 from the left. That's not 4. 3 from the left. And solve for the missing one. Okay? So what this goes to is when you use the practice exam, you will very likely not see the exact same question. That does not mean that just the numbers change. Okay? the content or the concept can also easily change through an algebra-based system. Okay? Other questions? Okay, well, we can end early, 2 minutes. Unless you got something to add, Greg.
There are writing questions.